morning to you all, and welcome to this webinar, Code of Practice for High Energy Photon Dissymmetry. I will hand you straight over to our chair, John Byrne.
You're muted, John.
Okay, I am now unmuted. Sorry about that. Okay, welcome everyone. I can see that there are still some people joining, but we can get ourselves started. Welcome everyone to this IPEM webinar, the Code of Practice for High Energy Photon Dissymmetry. If you were searching for the webinar on how to crochet a coronavirus, then you've definitely clicked on the wrong link. However, you are welcome to stay, and it may be more interesting. So my name is John Byrne, and as well as being a member of the Working Party, I am currently chair of IPEM Radiotherapy SIG, and so it's fallen to me to introduce this web meeting. In September, the 1990 Code of Practice was replaced by the 2020 Code, and 2020 Code continues to be based on the calibration service provided by the NPL. So the Working Party was made up of both clinical scientists and NPL physicists. And so with me on the panel today are Andrew Nisbet, chair of the Working Party, David Eden, who will present a summary, Russell Thomas, and have we got Graham from the NPL, and also yes, on the Working Party, we have where Simon Duane, John Frame, Mark Gratta, and Natalie Thorpe, who unfortunately we couldn't find a day when everyone was available, so they are not joining us today. So the webinar is up to 1 hour long, and David Eaton will present for maybe 25 minutes. If you attended MPEC, then you might recognize some of those slides as David introduced the Code of Practice there. After David's presentation, there will be an opportunity for questions. Please submit those questions in the Q&A feature, which you can find at the bottom of your slide. If you move your mouse, it should pop up. The Q&A feature then that allows, rather than the chat, because that Q&A feature makes them all in one place, makes it easier to manage, and we can tick them off. So please use the Q&A feature rather than the chat. I believe everyone should be able to see all the questions, so hopefully that will help to avoid duplicate questions. I'll try and look at the questions and pick representative questions if there are people trying to ask the same thing. So I'll coordinate the questions and try and get them answered, hopefully answered. We have 3 questions already submitted before the webinar started, so we'll definitely have something to talk about. Just before we start, I'd like to thank Candy at IPEM for arranging this. We all simply turn up, but there is a lot of technical and admin work that goes on before today, so thank you for that, Candy. The webinar will be recorded and will be available to all IPEM members via the website at some point. There's clearly lots of people registered, 220 so far in today, so there's clearly a lot of interest, and I hope you'll find it useful and informative. So David, if you're ready, I shall hand over control to you, and you can present. Hopefully, does Candy have to do that to give David the screen?
No, hopefully that should be coming up. Someone give me a thumbs up. You can see that?
Yeah,
Good.
That's all fine.
Okay, so I'm going to give you a bit of an overview of the new code, a little bit of historical background, and then as John said, we'll have time for questions at the end. So this working party, as John's mentioned as well, was made up of a number of individuals all around the country. So key individuals from the National Physical Laboratory, but also clinical physicists from a range of centres with a range of different equipment. And we really want this code of practice to have a broad applicability, and part of the reason for designing it was to make it hopefully ubiquitous. So I'll just start with a little bit of history. It was quite interesting thinking back to the history of radiation dissymmetry, and in the early days, I mean, getting on for 100 years ago, really, the emphasis was on the biological or the chemical effects of radiation. You may know that Pierre Curie, when he was discovering radium with Marie Curie, he decided to experiment on himself. So he would strap bits of radium to his arm for different lengths of time and see how red his skin went. So I guess that was a form of experimentation into early dissymmetry. And some of the radiobiological work, for example, Claude Rego working out fractionation schedules by balancing sterilization of ram's testes against skin reactions, was really focused on the biological impact of this new mysterious ray. But it soon became clear to physicists that something a bit more objective and a bit more easily a bit easily measurable was needed. So again, this was interesting to learn. The first ever meeting of the ICRU, I guess you've read many of their reports, was back in 1928. And one of their proposals was to set up a standard unit of the quantity of X-rays. And they defined that unit in terms of exposure. So the amount of dry air that would be ionized by a certain amount of radiation and produce a certain amount of charge. And that unit was named after Röntgen, who discovered X-rays in the first place. So this was a big step forward in standardization, but it still lacked the direct quantification of dose to tissue. This was still dose to air. And for many years, exposure, dose to air, persisted as a quantity that was easy to measure, but didn't necessarily relate that closely to dose to an individual who might be undergoing some sort of radiation treatment. So spin on a bit, and in 1940, the chap on the right-hand side, Hal Gray, who was based just up the road from where I am now at Mount Vernon in Northwood. So he proposed the gram Röntgen, which was an actual measure of absorbed dose to tissue. So an increment in energy per unit volume of tissue equivalent to what would be caused by 1 Röntgen of radiation in water. So then we spin on a little bit further forwards, and in 1953, the ICRU formally recognized absorbed dose as the best measure of absolute dissymmetry. In those days, it was still the rad, so it was still in centimeter gram second units. And finally, in 1975, they moved across to the SI unit of joule per coulomb, which we know as Gray, named after Hal Gray. The other interesting aspect to look back upon, and I guess this is before the times of many, if not all of us on this call. So when was the first UK code of practice? Well, looking back through the archives of PMB, we find that in 1964, there was a code of practice for the dissymmetry of 2 to 8 MV X-ray and cesium-1 through 7 and cobalt-60 gamma ray beams. Now, this code of practice was based on a standard 2 MV X-ray beam produced and sited at the National Physical Laboratory. And apparently by this stage, if you read this code of practice, the majority of clinical centres were using the MPL as a service to calibrate their local equipment. So we see many of the hallmarks of a modern code of practice, even in these early versions. Now, at that stage, remember, we were still dealing in exposure, so you had to do an indirect method using conversion factors for your beam quality, for your chamber. But some of the things that we would recognize as being part of a modern code of practice were still there, using a secondary standard as a calibration transfer instrument and not using it for routine work. It recommended measurements in a water phantom or in some sort of solid equivalent. Now, there were a couple of extensions to this code. So 1969, it was extended to use in using the cobalt standard beam and also a much wider range of energies. So in those days, I guess it was felt that much higher energies might be useful in clinical practice. I think we've since realized that 35 MV is a bit high really for our purposes in radiotherapy. Maybe even above 15 is unnecessary in many settings. But at this stage, the full range was available, but again, through all these different conversion factors. We fast forward to 1983. This is maybe getting slightly more into the living memory of some of us. There were revised conversion factors based on all sorts of Monte Carlo, Bragg-Gray cavity second order perturbations. And at this stage, the NE 2560/2561 instrument was recommended as being the only instrument that you should use as a secondary standard in this code. So to try and increase consistency. Now I had the pleasure of working one of these when I was a young physicist. They were a nice object, if a little bit bulky. This nice wooden box electrometer where you do the balancing. It's all quite fun. And actually the chamber is very similar to the chamber we use today. We'll mention that a bit later. So the code that you're probably all most familiar with is the 1990 Code of Practice. That's what it's become known as. And this is now based on two sets of beams at the MPL, a cobalt 60, and a range of megavoltage X-ray beams produced by a linear accelerator. It used tissue phantom ratio as the beam quality specifier. So we don't just trust that one 6MV beam is the same as another. We need a more accurate description of the beam quality, which even in itself is a reduction from the full spectrum. But for the most part, it works pretty well in terms of defining a beam in terms of a single number. And this code of practice was quite revolutionary in that instead of relying on exposure factors and conversions from exposure, it involved a direct calibration of absorbed dose. So using a graphite calorimeter to measure temperature rise and then converting that to dose to water in the chamber that was being compared. So the real hallmark of the MPL and UK IPSM code of practice is that it doesn't require conversion factors for all the local beam qualities. If you read AAPM TG51 or the IAEA TRS 398, so they generally expect that you will calibrate your chamber in a cobalt beam and then you will apply standard factors for your chamber type to apply that to a different energy of beam. Whereas the MPL approach takes that step out by measuring at a range of clinically realistic beam qualities. And we believe that this has led to very high consistency in terms of audit results into comparisons of one centre to another around the country. There's a couple of graphs that illustrate this. So on the left-hand side, you can see a range of interdepartmental audits over different years. And actually from the left-hand side, which was an excellent audit of its time, looking at the whole nation back in the late 80s, there is a broader spread of results than there was in a UK-wide audit just 10 years ago. And actually the spread is comparable to MPL audits where they go out and measure in a centre, which you would expect to be more consistent. And you can see in this data from Russell Thomas that looking at MPL audits to different centres, the agreement is generally improving as we go to the right-hand side. There's a greater consistency from one centre to another. And we believe, and the Working Party, maybe you do too, that actually the UK has one of the most consistent, one of the most robust dissymmetry communities, perhaps in the whole world. So you may be thinking, well, why do we need a new code of practice? The 1990 code has served us quite well for best part of 3 decades. But in that time, there have been some changes. So in my department at Guy's, we have a tomotherapy unit. There are several CyberNAF units scattered around the country as well. And these are unable to generate a 10 by 10 centimetre field. So the previous code of practice established a reference field size, which was 10 by 10 centimetres. But what do you do if your machine cannot achieve that field size? There's also been a major report published by the IAEA, so report 483, which looks particularly at small fields and brings in a lot of formalism and nomenclature from previous works to try and more accurately define different types of calibration field. And it was also recognised that the 1990 code was pleasingly short, nice to read if you're a trainee, it's only about 4 pages long, but it was a little bit brief on more guidance on calibration conditions, both in reference dissymmetry, but also in relative dissymmetry as well, for example, many small fields. So on this basis, there were some addendums and additions which were brought out in the meantime. There was an addendum to specifically address tomotherapy back in 2014. And the very popular IPEM report on flattening filter-free beams in radiotherapy, which covered the whole range of aspects associated with these beams, had a section on dissymmetry, and it noticed that the evidence is that although we can apply results from the MPL clinical LINAC to flattened beams quite well, you can see these are all averaging about 1. For flattening filter-free beams, there is a systematic difference, that these beams have a different spectrum, even for the same TPR value. So we need a correction factor in there to account for the fact that our chambers will respond differently in a 6MV flattened beam of, I don't know, TPR 0.66 or something, to a flattening filter-free beam with the same TPR. So as a reminder, many of you will be familiar with this process. You've probably done it many times in your careers. This is the calibration chain. So we start with the primary standard, the graphite calorimeter at MPL, which gives us that initial step of absolute dissymmetry. So we, as a local clinical centre, will send our secondary standard off to MPL every few years. They will cross-calibrate it and give us some calibration coefficients for that chamber. When we receive that chamber back, we then spend a good amount of time on the Linux working through all our local chambers, which are typically a pharma type chamber, but they could be another design as well. And we do cross-calibrations in our local beams. And once we have those calibration coefficients for our local field chambers, we can then use those chambers to measure and potentially to calibrate the reference output in our local beam. And we might also use those chambers for relative dissymmetry as well in non-reference conditions. So the secondary standard calibration at MPL, you can read more about. There's some good descriptions on the MPL website with the dissymmetry course. This is the graphite calorimeter. These are some transfer chambers. And actually the design of the chamber hasn't changed much in the last several decades. It is a good chamber, it's well understood, it is robust. So although it's got a slightly different number, we now call it the MPL 2611 chamber. It's essentially the same design. Now, I'm going to put a few equations in. So there's obviously a lot more detail about this in the code itself, but just to explain the balance that we've tried to take in terms of the nomenclature. So we need to put in a few more subscripts and superscripts compared to the original 1990 code so we can understand what we're referring to with each particular term. But we've also tried not to be overwhelmed by little and large S's and D's and W's. So this is the equation for the secondary standard. So the dose to water in a particular beam quality Q will be the measurement corrected for influence qualities, and I'll come to that in a minute, in that beam quality Q, multiplied by the calibration coefficient for the secondary standard, SS, in terms of dose to water, also in that beam quality, as defined by a particular quality index. So beam quality is a more general reference to the full spectral description of that beam, but the quality index is the way that we can actually relate that to a particular number. Now you see that the 1990 formalism is still hidden in there. We have D equals RND is the 1990 code. We've changed R to M in keeping with the IAEA practice, so M for measurement rather than R for reading. But it is still in there. We just added a bit more detail to describe what's going on. So as I mentioned, we're using TPR, so the ratio of readings taken at 20 centimeters and 10 centimeters deep in an isocentric setup for a 10 by 10 reference beam. So that is our standard beam quality index, and that is what the equation and the graph that you get from MPL refers to on your calibration certificate. Now, what if you can't, or you have a different local beam, you can't reproduce a similar quality and size, field size of beam to the MPL reference beams? Well, you need this extra value to take into account spectral differences compared to your local machine-specific reference field. So this is a standard nomenclature now. So the local field, so say we have a 5 by 10 field on a tomotherapy or a 6 circle on a CyberKnife. So that would be our machine-specific reference field. And we will need to apply some sort of correction factor, KSS, which if you expand it out, it is this term here, because it depends both on the quality and the field size. And that will account for the differences for a particular chamber between those two situations. We've tried to tabulate some typical values. So the tomotherapy addendum included data for the MPL secondary standard chamber, and actually found that in a tomotherapy 5 by 10 static field, the factor is unity, given some uncertainties. I should point out there is a single mistake, hopefully the only one in the code of practice, which we're going to get a correction issued for. So in the current code, it says 0.03. Obviously, it should be 0.003. We're talking about a 0.3% uncertainty in that value, not a 3% uncertainty, which would be quite large. We've also included the factor that was suggested in the FFF report, so 0.997 being the difference between a flattening filter free beam and a flattened beam of the same quality index. In terms of CyberKnife, there is some data in TRS 483 that we have taken from, which suggests again that the factor is unity. There is a footnote which maybe needs a bit of explanation, which is that the factors in TRS 483 also include non-uniformity corrections. So if you include that, the factor is 1. If you do them separately, then you have two different numbers, 0.998, 1.002. So you just need to be a little bit careful if you're trying to look back to TRS 483 or if you're applying your non-uniformity corrections in a different way. But we can talk a bit more about that at the end if they're still unclear about that. So let's imagine that I have a 10 by 10 field available. Well, to calibrate my secondary standard or to come up with a calibration coefficient, I need to measure my TPR 2010, 10 by 10 in that local beam. But if I can't achieve that field size, then there is a fairly straightforward approach for converting from one field size to another. Based on some work done by Hugo Parmans a few years ago, he found this empirical relationship between the TPR 2010 for a certain field size S and the TPR 2010 for a 10 by 10 field size. So you can measure in a local field given some limits, but that would certainly include a 5 by 10 or even a 5 by 40 field for tomotherapy, 6 circle for CyberKnife. We don't directly address gamma knife in this report. That is a more specialized condition, but the formalism for this report should certainly be compatible with some additional data for gamma knife in the future, and there is work ongoing to address that particular machine, which has a maximum collimator size of 1.6 centimeters, so quite a bit smaller. So once you have your TPR 2010 for your 10 by 10 field, you can then determine your calibration coefficient from your certificate, and you can apply a KSS value if applicable. Now, as many of you will know, again, we need to correct our raw chamber reading for some influence qualities. And this approach essentially hasn't changed since the previous iteration of the code. We've added a little bit more detail on some aspects and a bit more clarification. And these are all the different things that you might need to correct for. So all these different K factors for different aspects of the environmental conditions or the setup. But as you'll probably know, most of you, there are two that we need to be particularly careful of, and that's the temperature pressure and the ion recombination, particularly for flattening filter-free beams. The ion recombination values can be quite large. We can be talking well over 1%. And we also need to be careful about the beam non-uniformity correction for our FFF beams. So if we have a relatively large chamber in a non-uniform beam, then there may be some correction, even if we have it on central axis. And there's some discussion of that in the report as well. The other factors, so many sensors will calibrate their electrometer and chamber together. So potentially you might have an electrometer calibration factor for your secondary standard, but not for your field chamber. But you will need to consider these factors, the same with humidity and polarity. They may well be unity, but certainly when you're setting up your initial values, you need to be aware of them and be sure that they are unity. So now we move on to cross-calibration, cross-comparison, in a local beam. We prefer the term cross-comparison to inter-comparison, but some people call it that. And that's the standard approach that many of us will be familiar with. You take your chambers, you can either position them side by side, or you can substitute them one by one in the center of the field. And that approach is recommended for FFF, as it was in the FFF topical report. Although we acknowledge that if you're able to demonstrate equivalence in your own local setting for the side-by-side situation, then that's quite sufficient to use that if that's more efficient for you. I also like the difference between these two pictures. So this is a phantom on the left-hand side, standard irradiation phantom that you can buy. This is what it looks like when it's new. And this is the one from Guy's that looks like when it's had several, I don't know, 1,000 grey whacked at it for a few decades, that it goes a nice shade of browny orange in the middle. So finally, once we have the calibration coefficient for our field chamber, we can use that to measure a reference output in our local beam. And again, that simply gives us the dose to water in that particular beam quality is the measurement corrected for influence conditions for that particular chamber and setup, times by the calibration coefficient, this time for our field chamber, dose to water in a beam quality with a certain beam quality index. Now, one area where we have gone beyond the 1990 code is to recommend certain calibration conditions. So as these relate to your LINAC monitor chamber. So you might not just measure the dose, but you might actually adjust the output of your LINAC to give a certain dose in a certain setup. And then we recognize that there are different practices and there have been changes in terms of historical practice. So in the past, many treatments were delivered with a fixed SSD approach, so 100 centimeters to the surface. And so it was typical to calibrate your machine with 100 centimeters to the surface of your block or your water phantom. But actually in recent years, the vast majority, if not every treatment, is given isocentrically. And in order to try and reduce the uncertainties and have a parity between our clinical conditions and our calibration conditions, we recommend isocentric calibration. Now, many centers are doing this with a few different depths. So typically you might use 5 centimeters for your low energies, so anything up to 10 MV, as a measurement depth that was recommended in the previous code, and 7 centimeters for higher energies, so 11, 12 and higher. But we recognize that some centers may also wish to follow a 10 centimeter measurement depth, which is recommended in the IAEA documents. I think a few centers in the UK are doing this, but we didn't want to be too prescriptive. And equally, you may wish to calibrate your machine so it gives 1 centigrade per monitor unit at, say, 5 deep or at 10 deep. That gives you a nice simple result compared to. But calibrating to 1 centigrade per monitor unit at 10 deep can involve changing the output of the machine quite substantially. And some manufacturers are more or less reluctant to do this. So there's certainly one center who've taken the approach of choosing a calibration value which is less than 1 centigrade per monitor unit. So for example, 0.83 per MU at 10 centimeters deep gives you a result for a fixed SSD setup at Dmax very close to 1 centigrade per monitor unit. So that the change in your absolute output from the machine is going to be minimal. Now it's fair to say that's also true if you do isocentric at 5 deep because they sort of cancel out. Now we're not saying that every center has to be doing this as of today. As of tomorrow, the code is perfectly usable and perfectly applicable without this. But we are encouraging consistency going forwards, and certainly at appropriate points. If a center were setting up a new site or a new set of LINACs that with a different B model, for example, that it would be appropriate to use these calibration conditions going forwards. So let me give you a worked example for a 10 MV FFF beam. So there are 3 or 4 worked examples in the code to try and illustrate what we're talking about. These are just indicative examples, then using numbers that we believe are clinically realistic, but obviously you should stick to your own numbers and trust those. So these are the steps I've been talking about. So we measure our TPR 2010, we've got a reading at 20 deep, a reading at 10 deep, and we take the ratio of those to give our TPR. Now we need to be careful because the ion recombination will be different for a different dose rate and therefore for a different depth in the material. But we also recognize that in this situation, although the difference is substantial, 0.4%, actually when you relate that through to the calibration coefficient, it actually has negligible impact on the calibration coefficient. So it's not necessary to correct your TPR readings for ion recombination. It is more accurate to do so, but actually the impact on the final result is probably going to be very small. So armed with our TPR number, we can then look up the value in the certificate. Because this is a FFF beam, we have our 0.997 KSS factor. We'll then do some sort of cross calibration in our Perspex phantom. So we've got some raw readings at 5 centimeters deep, which is the standard construction of these phantoms. Again, we've got different ion recombination factors because these are different chambers, different voltages. 360 is just the voltage that happened to be used for this example. It's not particularly suggestive. I know other centers use different amounts, 200, 300. So we'll get an intercomparison or cross calibration ratio, and then we can then use that using the equation I showed you to give a calibration coefficient for our field chamber. We then take our field chamber reading where we've applied the ion recombination, the temperature pressure correction for the particular setup, and then we get a dose to water at the end. So in this example, it's come out as 101.1 centigrade for 100 minus units. So that's 1.1% higher than our standard reference. And we may choose to leave that, we may choose to bring it closer to unity. And finally, I just want to touch on non-reference dissymmetry. So there's a really great wealth of information and detail about this in TRS 483, and we're not trying to replace or substitute for that report. I would encourage you to read it, but it is very long. And so we've tried to give a summary of the particular points that are most salient in the later stages of this code of practice in a section towards the end and in an appendix as well. So non-reference dissymmetry might include large fields. So one area I haven't really touched on is the plan class specific reference field. So you may have a machine specific reference field with, for example, a different field size or a different spectrum. But you may also have a machine that delivers radiation in a non-reference way. For example, tomotherapy units are typically calibrated to a rotational output, not a static output. So in that case, you will have another factor. This is the full expansion of it. It was called KFC in the Tomo addendum. I'm afraid KFC is closed for now. Maybe after lockdown, we'll see, but for the time being, we're going to use the full expression. And the Tomo addendum suggested that this was unity for the A1SL chamber. For small fields, the approach would be to daisy chain. So let me tell you a bit more about this. So when our cross-calibrated chamber is too large for the field, then we may need to use our field output factor in combination with a reference field dose, because we can't be sure that there's charge particle equilibrium if our field is smaller than the lateral charge particle equilibrium radius. So essentially the code formalizes what you've already been doing. So you measure an output factor. And if you have tables of output factors, if you know the equivalent field size, you can use that, but this approach is limited because the chamber response might be different between a long thin field with the same area and a small square field with different perturbations. So measurement is recommended. And we also need to be careful about the type of chamber. There's guidance in different tables in the TRS report as to the minimum field size and correction factors to use for different chambers and different machines. We can no longer take the ratio of ionization to be the ratio of dose because of perturbation, lack of equilibrium, and possibly energy spectrum response differences. So we need correction factors to apply in these conditions. And if the detector has a strong energy dependence and the spectrum is sufficiently different, then it's better to daisy chain. So this is where we have an intermediate field size. So for example, for some solid state detectors or pinpoint chambers with a steel electrode. So we use our small field detector in the small clinical field. That's our CLIN there, F-CLIN, Q-CLIN, and an intermediate field for which that chamber is still applicable, and compare that to an ion chamber that has been cross-calibrated in the reference field, and also we compare the two in the intermediate field as well. It's worth saying there's excellent guidance as well in the IPEM report 103, which is still available from one good stockist, and you may well have a copy in your department already. So the conclusions are we've tried to retain the strengths of the 1990 code, keeping a standard device, the MPL 2611 chamber, as our secondary standard. It is quite reasonable to use different electrometers now, and there was some IPEM guidance on that a couple of decades ago. We're still using TPR 2010 and a 10 by 10 field as our quality index. And MPL still, very nicely, provide calibration coefficients for a range of clinical beam qualities. And these beam qualities are from an electrolinac, so they are very similar to what you would have in your clinic, with some caveats around FFF beams. So we have extended the formalism to units that can't achieve that 10 by 10 reference field, and we've tried to provide recommendations for measuring dose both in reference and non-reference conditions. So we hope that it'll be still simple to use and applicable to every centre that wants to use it. And I would commend it to you. Thank you very much.
Okay, thank you, David. I think I'm back live. We can now open the floor for questions. As I said earlier, we do have 3 questions that were submitted before the meeting started. Unfortunately, I'm unable to copy those questions into Q&A, but I've sent them to my colleague Steve Loss. Steve, would you put those 3 questions I've emailed to you into the Q&A? Yeah. So the first question that's been submitted so far is from Jeff Hayes. It says, query, okay with 80 centimeter SAD calibration for CyberKnife, still isocentric approach, but intracranial treatment with 80 centimeter SAD. Does anybody want to pick that up? I don't see that there's a problem with that.
Yes, that's fine. And in fact, I think we actually state that in a footnote under one of the examples. So I think that situation is actually explicitly mentioned in the code of practice.
Second question from my colleague who's just left the room. Do the NPL take account in variation of K ion with depth in the TPR 2010 values quoted in the calibration certificates?
Sorry, I can't find the mute button. we certainly used to take account of the ion recombination correction when we did TPR on the old radiation dynamics LINAC. I'm not sure if they still do on the new values, but the new values will be taken as a consistent historical increase. So I don't know if Graham can comment on that. This is Graham now runs the service.
No, we don't account for ion recombination. But it makes no difference.
Yeah.
Those are on the
Steve Locks is
standard conventional beams.
So I think we've lost.
We couldn't hear anything.
Russell, have you got more to say on that?
No, just that it's a very, very small effect on the conventional non-FFF beams.
Yeah. So NPL don't account for it because it's a negligible effect.
Yeah.
So I asked Steve Locks to post the 3 questions that were submitted beforehand because I couldn't do that. So question 1 is one that David touched on. Could the speaker please explain the comment under table 1 of the code of practice regarding factors to use for the CyberKnife dissymmetry? How exactly are table 12 and 13 compared, and what is being demonstrated? As I understand the format laid out in the IPEM FFF report, there are 2 components. Firstly, beam spectrum, and secondly, beam uniformity. This means a factor of 9.998 for spectral difference and a factor of 1.002 for beam uniformity, giving a combined recommended factor KSS of 1. So that's what David alluded to in his talk. That is the case. It's perhaps not worded very well in the footnote of the table, but that is the correct interpretation as far as I know. David, do you want to say anything more about that?
Yeah, so the question is, and I guess we could have done it either way around. I suppose I was concerned that people would look at the IAE report, and when you work it out, the numbers you get from those tables is unity. But actually, there's a footnote to those tables saying these factors include the non-uniformity correction, see table 35 or something. So when you divide that out, you get a strict spectrum value of 0.998. So we could have put 0.998 with a footnote that it's also 1.002 for CyberKnife. I suppose as long as people are clear either way round. So I'm sorry if that's caused a bit of confusion, but yes, that explanation is correct.
Yeah. So the next question is, during the discussion on simultaneous cross calibrations, why is it recommended to only swap twice? I assume that twice as many measurements as a position A might potentially weight the geometric mean. Yes. Does anybody want to pick up that? I believe it should be symmetric. It's better to do A, B, B, A. But there should be an equal number of.
Yeah, I think the wording actually says at least twice. So yeah, yeah, I think it's getting that balance between the time it takes and what's actually needed. So by saying at least twice, if it's very stable to begin with, that's sufficient. But obviously, if you want to do it 4 or 5 times, then that's fine as well.
And the last pre-submitted question is, we have 2 Linacs with energies 610, 10 FFF and 15 MV. We currently calibrate all these energies at 5 centimeters deep, 95 centimeters FST. Would you advise that we recalibrate? I would say no, because if it's working, then don't change it, and there's always a danger of making a change. As David said, there's no recommendations on how to calibrate on the original 1990 code. And there are 3 good reasons for calibrating, for giving recommendations on calibrating. One is for consistency between centers, and that allows you then to compare doses under the same conditions, and you know that you're comparing like with like. The other is to recommend not doing it at Dmax, and the other is to recommend doing it in an area where applicability of NDW. So we give recommendations, and as David says, we're not saying you should go away and change things unless you are making an actual change anyway. You could change so everything is at 1 depth, and that the second recommendation to do it 10 deep with effectively 1 centigrade per monogy at Dmax would cover all those situations, but essentially you could calibrate anywhere with those 3 conditions holding, and you would still be safe. Does anybody else want to say more on that?
Yeah, I think it came in, it was in one of the earlier codes. I'm just looking back. I think in 1969, so in 1964, it suggested to use a 5 centimeter measurement depth. So the main thing is don't measure at Dmax, because it's very sensitive to position. You're not in charge particle equilibrium. And actually the thought at that point was that 5 centimeters is quite close to a clinical depth. But then in 1969, when they went up to 35 MV, they said, well, actually, it might be better to have 7 centimeters for 11 to 25 MV beams and 10 centimeters for more than 25 MV. And the reason they gave was that better matches the depth of clinical interest. So I don't think there's necessarily a kind of a measurement accuracy issue. It's more trying to equate that. I mean, as I say, we don't use anything much above 18 these days. So if you felt that 5 was sufficient for your 15 MV beam, maybe that's simpler than having a different depth just for that 1 energy.
Okay, Andrew Riley has got a few questions. Do isocentric conditions for monitor chamber calibration really need to be mandated by the code, or could there be flexibility on this?
So again, I think this is a point we did discuss at length within the working party, but I think we came to consensus that we felt there was a strong argument for recommending a move towards isocentric calibration, that the benefits did outweigh any disadvantages, and so that was a clear recommendation that I think has come out from the code of practice. Again, I don't think it's within the working party's remit to provide guidance on what considerations need to be taken in moving from a fixed FST to an isocentric calibration. Whether the special interest group wants to consider workshops for that, I think that will be up to the special interest group themselves. And the final point Andrew asks, will manufacturer guidance be updated to match the new code? Again, I don't think that's necessary, because as David alluded to in his talk, and I think as other centres use, you don't need to calibrate it at 1 centigrade per monitor unit at that reference depth. You can calibrate it at less than 1 centigrade per monitor unit. So all manufacturers of Linux or other treatment units should be capable of delivering, or the code of practice should be applicable to any manufacturer. I don't know if anyone else wants to add to that.
No, I've read the varying guidance, and it doesn't seem to me to say anything other than don't stress the machine out, really, and nothing that we're saying here will stress the machine out or will put it in a stressful situation. And yes, as you said, if there's a desire within the red therapy community to have a workshop for helping people to recalibrate, change from fixed SSD to isocentric, then yeah, they can ask for that. If there's enough of interest, then certainly the SIG can organise that. So Virginia Marine and Anaya says, could you please confirm / give an estimate of when the IPM code of practice for high energy proton beams will be published? Thank you very much. That's not a question for us. I'm not.
I can give some indication of that. We're hoping to have our final draft of the code itself by the end of this year. Well, I was hoping that was going to be the case. It has been further delayed by certain conditions that have happened internationally, but I think we are very close, and I would hope that it will be published in 2021.
James Early says that question is missing the end about whether we should recalibrate 15 MV. I'm not sure what that means. Maybe you could resubmit the question fully. I think we've answered that.
I think what we don't want to do is create any confusion in any departments, do we? It would, from my point of view and from the point of view of MPL, I think it would be lovely if everybody did the same thing. But historically, in a lot of departments, there's been different ways in which things have been set up. What we don't want to do is create any confusion. There was the recommendation to calibrate at 5 centimetres deep for below 12 MV or whatever the TPR value was, and 7 centimetres above. But there's been, some hospitals have taken a pragmatic approach not to create confusion in their department and only stick to 5 centimetres. By giving the option to do it at 10, I think we go into line with what a lot of treatment planning systems are also doing. And I think, as John said, we'd answered the question about perhaps moving across later on. Should you be looking at it as a whole department move?
I think we've answered how well does the variant tree beam perform under this calibration. It shouldn't cause it any problem. We have done it for many years. calibrating at less than 1 centigrade will possibly cause problems. Are we setting ourselves up for an error? Can we have more guidance on, do we all choose e.g. 0.8 centigrade per magnitude? I can speak for Newcastle, where we have for many years done all our calibrations with measurements at 10 centimeters deep, and it causes a lot of simplicity in setup and QC, as well as calibrating the LINAC. We've always set up so that we calibrate the LINAC to give very close to 1 centigrade per Monit unit at Dmax. So it's just the physical conditions of making the calibration, but the dose per Monit unit that the LINAC's delivering is the same as if you calibrated it at Dmax or any depth where you set the dose per Monit unit to be close to 1 at Dmax. So I don't believe that it never caused us a problem. I believe it is relatively simple to do without introducing errors. But perhaps we could have a workshop if there's enough people want to make changes and are concerned. And Sheila's also saying, particularly for a variant true beam. We use variant true beams, and we have done this for many years and never had a problem. Nicola Twyman says, the code states regular constancy checks should be performed on all chambers. Yeah, thank you, Nicola. Oops, we are currently reducing strontium checks odd chambers. I know others don't have strontium pots anymore. Is this really needed? I think that the constancy check question is still valid. Your question is probably, how do we decide whether the chambers are performing consistently, and whether strontium is the right way to do that is another question. Does anybody else want to pick up on that?
I'd agree with that, John. I know that some centres don't have the strontiums, and they tend to check the histories and the performance of their chambers against other chambers, and that's a way in which you can avoid the problems of check source measurements.
Margaret Burr is saying, is there any audit of centres using the small field approach by NPR, and if so, is it performing well?
So I'm not sure. There have been some audits on from RTTQA that have looked at the SRS audit, for example, and things like that. We don't have a specific reference audit for small fields yet. We were developing one for Gamma Knife, which we could possibly move, do a similar thing for the small fields, but unfortunately, we just don't have the staff to keep that going at the moment, because the girl that was running it has gone off on maternity leave.
Paul Evans has got a good question there. We have 3 questions in the Zoom chat rather than the Q&A. Regarding the chamber-specific quality correction factors tabulated in TRS 43 and measuring dose in small fields, these are tabulated only for a range of detectors, not all, but only at 10 centimeters deep. How would you adapt these factors for other depths? Also, what values would you recommend for measuring intensity modulated fields? Somebody want to respond to that? I think the general answer is, if you do not have the correction factors tabulated, then you have to measure them. And then if you measure them, it would be good if you could publish them. Richard Clements, I had always assumed that the NPL calibration was done at 10 centimeters SSD, sorry, 100 centimeters SSD. Was then moved to isocentric calibration recent? One for Russell.
I think Graham's responded to that in the chat actually, because Graham states no, it's always been 100 centimeters source to chamber distance, I believe, for photons, and 100 SSD for electrons, as long as we've had a clinical LINAC. Yeah, and I think that was the same before the clinical LINAC as well. Certainly for photons, that's what we've always done while I've been there.
Neil Richmond's noting in the Q&A, APM TG71 recommends reference to those values when calibrating at 10 centimeters deep. Thank you, Neil. So if there are no more questions, then I think we may have come to the end of our webinar. We've got 2 minutes now to the hour. So I'd like to thank you all for attending and making it a successful meeting. I hope you got something out of it. Thank the attendees and the panel members, of course, for being in the firing line. And a special thank you to David for doing the hard work of presenting. Hopefully it's been useful and some of your questions have been answered. I'd like to thank IFM again for hosting this and for arranging to have the recording available to members. Candide, have you got any time scale for that?
We'll get this up onto the website as soon as the recording has finished. It'll probably be in a week or so, but it will be available there. So just keep an eye on the website and we'll pop it on the front page. Otherwise, just to say thank you all very much, and thank you, John, for chairing it.
Thank you. So we'll bring this meeting to a close.
Thank you, everybody.